So we have introduced the notion of Hodge number and Newton number. Now let's introduce what is called Newton and Hodge polygon. And then we do a related exercise, doing some examples to describe those polygons. So let's first introduce those notations and then compare these two things or relate them. At D filtered phi n module we have defined the Newton number. And Hodge number. There is a useful way to visualize this invariance. These are invariants actually, yeah, if two filtered phi modules are isomorphic, they have the same Newton number and Hodge numbers, right? So, namely, the Newton polygon is denoted by Pn, and the Hodge polygon is denoted by Ph. So by the Dieudonné Manning classification, made in previous exercise, we know that for a non-zero isocrystal, D over K0 it has a unique decomposition. It has a unique decomposition. Alpha rational numbers, D of alpha. This is only a finite direct sum. Only finitely many D alpha non-zero. Where the alpha is the part of the subspace of the slope alpha. Suppose we have alpha 1, alpha 2, alpha s out all the alphas such that d of alpha is not 0. And we write v of j equals dimension of k0 d of alpha j. Definition: the Newton polygon denoted by P and D is the polygon with breakpoints zero, 0, and then for any fixed j with 1 plus v to deal with j, this is the x coordinate, y coordinate is which is also times the slope with 1 alpha 1 plus etc. with j alpha j. So how many breaking points? 0, 0, and then for any j from 1 to s. So s is the dimension of, sorry, s is the number of slopes. Thus, the endpoint of this Newton polygon is h, which is the dimension of d, and then Tn of d comes from the formula to compute this Newton number using slope times dimension of the corresponding d alpha j and the summation, right? And so we draw a picture, which means we have starting 0, 0, and then slope from small to big. So it's at the beginning it's negative, and then it become more and more closer to 0. At some point it become positive, and finally it reached the point h, t, n of d. Point the middle, this is v1, slope alpha 1. This is v1 plus v2, this is slope alpha 2, so alpha 1 smaller than alpha 2, etc. And slope alpha n, sorry, minus 1. In our case, this is slope alpha s minus 1. Those are the breaking points. It's just the example of how it works. Similarly, let's define Hodge polygon, but before that, let's give a remarkable example. A non-zero isocrystal d over 0 is isoclinic of slope alpha if and only if the corresponding Newton polygon is just a segment. If you are only a segment, it will tell that it means that you only have one slope. Always start at 0, 0. With slope alpha. which is to say that d hat this change criterion we find this change isoclinic. Slope alpha. Now let I1, I2, IS be such that field IJ decay over field IJ plus 1, which is sub module is not 0, which means there is a jump. And for this, we know the important thing is the dimension of the gridded piece. So field IJ quotient field IJ plus 1 for each breaking index. Now let's define the Hodge polygon. Pn of D is the polygon with breakpoints 0, 0, and similar as before for all the Hj, with j coming from 1 to s. X coordinate is the addition of all those dimensions, which are Hj, with y coordinates this index times this dimension. As a result, the endpoint of this P and D is thus all the dimension add together gives you the dimension of D, which is again H, and by the formula of the alternative equivalent formula, this breaking jumping index times the dimension of the gridded piece gives you Hodge number. And so you could also draw a picture of this. Very similar. Starting breaking point 0, 0, and then slope I1. So those breaking index become the slope. This is H1. H1 plus H2, slope I2, then finally H PHOD. This is already the summation of all those. Dimension, this is slope, IS. So natural questions to compare this. Remark. The formation of Pn and pH is unchanged by the scalar extension. K0 to K0 on ramified completion. Second remark, the admissibility condition. So this is an exercise 91, I guess. Well, we define what is called filtered admissible filter fine module, or maybe just the last exercise, maybe. Yeah, to check it. So the admissible condition there tells that D is admissible if and only if for all subobjects D prime contained in D, we have Hodge polygon. So always under Newton polygon, which means geometrically the Newton polygon lies above Hodge polygon. Important remark 3. This is a proposition. Maybe someday we give a proof of this. So this one due to Fontaine gives you equivalent statement of this admissibility. So let D be a filtered key vector space with Frobenius, and say a filtered fine module. With finite dimension and bijective Frobenius. The following are equivalent. So there are two statements. The first says for all subobjects D prime contained in D, Hodge polygon is low Newton polygon. Which is the one we just described. Secondly, they said that for all subobjects we don't have to look at the whole picture. We only have to look at one point, the rightmost endpoint of this Newton polygon lies on or above the one for Hodge polygon. So instead of looking at the whole picture, you only have to look at endpoints. Okay, we're going to do some exercise. Basically, we want to compute some examples or just describe some easy examples. The first example is look at trivial filtration. So the exercise asks you to compare this. For this trivial filtration, how about this? How about this? Right, compare these two polygons. So let D be a filtered finite module such that it's finite dimension as K vector space, and Frobenius is bijective. We consider the case special case 1, the filtration structure. Is trivial. Which means fit 1 is 0. I mean, by that twist, you can always, if it's R, then you just, by that twist, you can turn it into fit 1 equals 0. So I will end at the very end the remark on this Ted twist. Let's first finish the proof. So up to Ted twist at the beginning, this tells field 1, field 0 of D is D, and field 1 of D is 0. So this is what we call trivial filtration. Then suddenly drop down, no matter what's the dimension. These hence the case in which the Hodge polygon is just a straight line. In this case, by convexity and agreement of both endpoints, it follows that P and D equals PH. Newton polygon, the Hodge polygon coincides. So in terms of isoclinic decomposition, there is only one slope. Hence, without any hypothesis of the dimension of D as a key vector space, we must have the monodromy is 0 and Frobenius is isomorphism with pure slope 0. So I hope you have understand the argument here. If not, so let me add some more details. So why can we conclude that it must be this breaking point, this straight line? So here what do we put? This is the dimension of D, which is n here. So why this is the case? Because what is T? What is the Hodge? What is the new? Let me see. Hodge number of D. It is the one of the jumping index, right? Here we have field 0 equals D, and field 1 equals 0. And so this is exactly 0. Right, that's the only jumping. That's the only jumping index actually. And so this forces this to be 0 because this is the end point is THD. And this should also be the Newton number of D, because this trivial filtration should correspond to the admissible case. Admissible. and then this forces the slope to be 0 also. Wait for a while. Or maybe we are not using any admissibility, we are just by definition of Newton number. So let's say if we want to use the formula to compute the Newton number, then what would it be? To compute the Newton number, you also have a formula which tells you that. You could use the dimension of each dr phi and then you times with the slope. Right. In times with the slope. So for one-dimensional, the Newton number is defined to be the valuation of the p-adic valuation of this sentence eigenvalue of lambda for Innis. Wow, for finite dimensional one. So those slopes correspond to the evaluations of the corresponding eigenvalues of the Frobenius sentence. When this filtration is trivial, we could easily have a picture of this p-adic, but for Newton number, yeah, really, how did we conclude? So, remark is that if this is the case, then the sub-objects are phi stable subspaces, each of which has Hodge and Newton polygons. That coincide. As segments along x-axis. Hence, admissibility criterion is always satisfied. So here we're just saying that. So let me modify a little. So I'm talking about admissible trivial filtration, and then this is clear. So when you have this is 0 and this Newton is always below, sorry, this Newton and Hodge coincide. This is by definition of admissibility. And then this force is is forces for any submodule. Forces for any submodule d prime. The Newton number is always bigger or equal than the Hodge number because it's always 0 by the convexity. The definition of admissible, we have this identity, and then the Hodge polygon and Newton polygon coincide. Because this x is just the dimension of d, and so everything just compressed to a segment. And the criterion for admissible is to check that for any submodules, this Newton number is always above or on the Hodge number. It's equivalent to check by the propositional function we describe for each submodule. You just check that. The endpoints of the polygon is equivalent to check the polygon itself lines up. While you could think of this as the example of yeah, I think this is the case. Otherwise, I don't know how can you compute directly this Newton number just from the information of filtration. But the Newton number really depends on not only the filtration but the Frobenius structure, and then gives you the isocrystal, isoclinic decomposition, right? Yeah, that's what in my mind at this moment for this. Okay, so let's continue second part of the exercise. Let's look at the admissible filtered finite modules of dimension 1. So describe those. So let D be filtered finite module over K. With dimension D equals 1. Such that Frobenius is surjective, is bijective over D. Then we can write D equals K0 generate span by D for some D. And then we look at how it's Frobenius acting on this basis element. Then this n must be 0 because this nd is a subspace, because it's linear, it's a subspace of D, so either it's D itself or it's 0, but it's nilpotent. And so force it to be 0, because otherwise it will never be nilpotent. If nd equals D, then this will tells and to whatever power sd equals D, and this will be contradicting to nilpotent, right? Good. Now let's write dk defined to be this change of d to k. It's one-dimensional over k, and there exists integer r such that if you look at the filtration, there exists some r such that this is jump index, right? So clearly, then this Newton number of d is just Newton number, because we're talking about dimension 1, so Newton number of d is just the only jumping. Sorry, the Newton number is p-adic valuation of lambda. And the Hodge number is the only jumping index, which is r. Therefore, d is admissible if and only if p-adic valuation of lambda equals exactly r, because this is only dimension 1 is only one segment, right? Okay, so let me put final remark here. I'm not going to prove it, but just this is still example of Newton polygon and Hodge polygon. So let E be an elliptic curve over K. With good reduction. Let D be the filtered phi module over K associated to E. With its natural Frobenius. And dk was also filtered then. Then we claim that this dk is the same for all E. Actually, we haven't explained how to associate to elliptic curve filter phi module, but we'll see that later. There's some category equivalence between the semi-linear algebra thing and the representation things. So this dk is the same with the structure as a two-dimensional k-vector space with graded 0 and graded 1 piece each being one dimension. And so what does this tell us? This is telling us that if we draw the Hodge polygon for this elliptic curve E, its breaking point is starting at 0, 0, and then it's dimension 2, but the first part is here 1, 0, and the second part is here 2, 1. We see the Hodge number because, as we said, so this dimension of this is 1, dimension of graded 1 piece is also 1. Once you know this dimension of graded piece, what you have to know is the position, jumping position, right? So which means you have field 0 quotient field 1, field 1 quotient field 2. This is telling this is D, and then this is some dimension 1, this is dimension 1, this is 0, and so the jumping position is 0, 0 times something, and then that dimension is 1, right? Similarly for the Hodge, for Newton polygon, how do you compute? So starting breaking point, dimension is 2, and you care about the p-adic evaluation of those eigenvalues. Right, we didn't know how to describe this yet. This is one thing we could know. So how about the Newton polygon? So this is the structure of the isocrystal. So let's say in contrast, the structure of D and an isocrystal depends on whether the reduction, so this is special fiber of E over residue field K is ordinary or supersingular. So by some results, so this is some research paper results. Let me mention one of the reference for you. So for example, look at, there is paper by Pierre Bachelot, Breen, William Mason, Card, Dieudonné Cristalline. Lecture notes, mathematics Springer, 1982. If you look at there, you could see they proved the following result, which tells that this Newton polygon looks as above. So here I'm going to draw it. There are two possibilities. Both endpoint here. Where this is the ordinary case. And this is supersingular case. So in particular, we see that the endpoints of this Newton polygon and the Hodge polygon coincide with the same endpoints, and the Newton polygon, in whatever case, is all above this Hodge polygon.